is going to be the building blocks of everything that we're going to talk about for deep learning. Then we're going to talk about what makes machine learning different than things you already know, maybe optimization or something. Then we're going to talk about a few of the buzzwords in machine learning, neural networks, backprop. What are these things really? What's going on? And then we're going to go all the way into deep learning, the new, latest, and greatest cutting edge. We're going to give you the definitions of what these are exactly and give you some examples of what they are and how they work. Okay? So, where better to start than with a definition? Machine learning, a machine learning algorithm is an algorithm that is able to learn from data. So that it feels real cool and it sounds great, but it's pretty much entirely useless from an academic perspective. That's just a real hand-wavy explanation. So we'd like something a bit more rigorous. And we've got a nice quote here. This was defined back in 1997 by Mitchell. This is used in a lot of deep learning, machine learning textbooks. So this is going to be the framework that we're going to build from. Now I'm going to take just one moment to reiterate how important it is to approach machine learning from this lens. Any problem that you're working on, even your projects here today, if you can take a step back and recast it from this perspective, you'll be able to identify what you're trying to do, how to do it, and the little variables and the knobs that you can twist and turn to make it work. Okay? So, a program is said to learn from experience, which we're going to call E, with respect to some task that you're trying to perform, classification, self-driving car, robots walking, whatever you want. And performance measure P, if its performance at the task gets better with more experience. Okay, so we have this notion of tasks, experiences, and performance. So we're going to start it off like this. Experience, this E is going to be data. So as far as machine learning is concerned, experience is data. And you can even abstract this away to be, as humans, what are the experience that we get? We get input, output. I see something, I do something, and then I get reinforced from what I did. These are data. This is good, this is bad, etc. So experience is data in machine learning. Okay. Our task is what it is that we're trying to perform, and we're going to see that this is essentially just a function. We're going to be training some function to do a specific thing. Okay, so this is going to be a function. And then our performance is going to be our cost function. This is what allows us to control what the function learns to do. Okay, so this is going to be basically our cost or something along those lines. We're going to define these a little more rigorously in a minute. So, a few examples. Tasks. What are some tasks that we can think about trying to do? Some of you even have projects that are attempting to do things like this now. You have classification. People are working on looking at videos and identifying this has something or this doesn't have something. This is this type of a thing or this is not this type of a thing. Transcription. Taking audio files and then transcribing it into text. Anomaly detection. Oh, somebody's using my credit card in Hoboken, New Jersey. Never been there, so it's probably not me. I hope my credit card company is able to figure that out. And then synthesis, being able to create new things, generative models, the latest and greatest. So these are things that we research and we'll talk about at the end. So performance, this is very difficult because what does the performance measure even mean? Like, let's say I'm trying to translate from one language to another. Do I just penalize it if it misses one specific word, or do I somehow penalize it on the context that it's trying to relate? I mean, if any of you have studied a foreign language, oftentimes there isn't even another word in that language to directly translate the one word that I'm trying to translate. And sometimes it's multiple words. So how do you do this mapping from one to many, many to one, and back and forth? So these performance measures are very difficult. And this is one of the places that people spend a lot of time in working. And again, experience is just data or feedback if you're dealing with reinforcement learning. But we're not going to dabble with that. That's a bit of a different field. All right, so roughly speaking, machine learning, remember we're going to move on to a few other things in a minute, but machine learning can be broken into three categories. Supervised learning, unsupervised learning, and reinforcement learning. Does anybody want to just take a stab at what some of these things are and what the differences are?
I believe supervised learning is when you have a certain goal for your machine to meet in mind, and you train your machine to reach that goal. I think unsupervised learning is when you just let your machine do its thing and discover and just tell you whatever it finds on the way.
That's a pretty good first stab at defining it, yeah. I might refine it a little more, and instead of saying just a goal, because unsupervised learning has goals too, but I would say labels, right? So for each element of data, for each element of data, we have a label of what this data is. Is it good? Is it bad? Is it a cat? Is it a dog? Is it credit card fraud? Is it not credit card fraud? Whatever it is, okay? Unsupervised learning has no labels, and reinforcement learning is in a whole world of its own. Essentially, you get feedback. So the idea is you take some autonomous entity, put it in some environment, it just does what it does, and then it gets reinforcement based off of its experiences. So it's really kind of a whole little world in its own, which we're not going to talk too much about today, okay? So labels, no labels, and then reinforcement. So now let's take a few examples of what these are, and then we're going to refine the definition, and then we'll move on to what the difference is between this and other things. So, classification. Classification is, I have a data set, this is supervised, so I have labels for them, and my goal is, given some new element that I've never seen before, I would like to classify it as one thing or another. So this can be broken down to something as this. We have a whole class 1 that exists in some space, and they're strewn about in some two-dimensional space like this. We have some other class strewn about in this two-dimensional space like this, and the goal in classification is to learn the partition function that separates the two classes. Then, once we have this partition function, we say, given some new element, which side of the partition function does this new element lie on? And from that, we can infer what class it belongs to, okay? So then we also have this thing called regression. So what's this? This says that there exists some true unknown distribution. Let's say, for example, this is the vertical axis is price, and the horizontal axis will be the year of a car. All right? This looks like this might follow this trend. So the really old cars, these are super expensive. They're classics. Then you get like the sort of modern cars. Nobody cares too much. But then you get the brand new cars, and these are super expensive again. Just a hand-wavy example. So there exists some unknown distribution governing these properties. But the real world never follows these exact distributions, and there's stochasticity. Maybe this guy really loves his car and decides it's going to be worth more than it actually was, so he's trying to sell it for more. And this guy, he doesn't really care. He's moving. He needs to sell his car. He's taking off to New York tomorrow, so he marks it for lower. So now we have a bunch of training examples of a certain car and a price. And our goal in regression is to fit some function through the observed points to best approximate them. And the goal of this is, now that I have this function, I can say, given some new x that I've never seen before, I can say what should be the price of this car. So you're learning the general properties that describe the prices of cars. In other words, it's an approximation to this unknown true underlying distribution. Okay, so these are both supervised. What do we have in common? We had labels. Given some x, we had a price. Given some data element, we had a class. So what happens when we go to unsupervised? Let's take a look. Unsupervised, this is going to be the unsupervised corollary to classification. So we're given a bunch of data in 2D space. This is contrived, I know, but this gets the point across. The goal is, given a data set, can we just find structure in the data set? We'd like to tease apart the underlying properties of the data set. Once we've done this, we can see now we have clusters. Now that we have clusters, we can do classification. So you can see how this is a strictly harder problem. You can't even begin the classification problem until you find that there exist clusters where there are classes even in the first place. Maybe you have a data set where there are no clusters, and you try and cluster it and find, but it's just one big Gaussian distribution. You can't do classification for something like that. All right, and now what about the corollary for regression? Well, that in unsupervised learning is called manifold learning. That is trying to shoot directly to that underlying distribution. So we no longer have relationships between these variables. Before we had like a car, a year, and then a price. Now we just have a bunch of points in space. We don't know the relationship between them. We're not trying to find some functional mapping from one to the other. We just have points. And the question is, does there exist some underlying distribution that gives rise to this data? Can we find that thing? Okay, so this is the big level perspective that we're dealing with in machine learning. So, the question is, what I've described to you currently is essentially an optimization problem. Okay? So what do we mean by that? What I mean is, we had some function, we had some goal, y is equal to the output of some function of x. We had some data set, x is an element of some large data set here, and the goal was, I want to say I have a cost function, j, of y and maybe some label, y hat, we'll call this y hat, and we also have here a label for this. So x and its label. We give some x, try and guess what the label should be, and now we have a cost function between the actual label and what our guess was. And what we'd like to do is just minimize this with respect to some parameters that this function is parameterized by. Okay? So this is basically everything that I've described so far. We have some data, and their labels. We have some function which I'd like to take some new element and map it to the correct label, and I want to minimize the distance or the difference between our guessed label and the correct label with respect to the parameters of our function. Okay, that's optimization. So what is the difference between optimization and machine learning? Why are we not all over in mathematics learning machine learning optimization right now? What's the difference? Anybody? Anything?
I mean, I would think, well, with optimization, you have some, well, you basically know your input.
It's pretty, you're on the right track. There's a little more to it, but yeah, that's the right line of thought. Can anyone add to that, maybe? What's the difference between optimization and machine learning?
I suppose with optimization, you're simply finding the values that give you the least difference between an actual value and another value, but you're not really doing anything with it. You're not feeding it back into the algorithm and improving anything. You're just finding a value.
You all keep like dancing around it. You're all sort of have an intuition, but you're not saying it exactly correct yet.
I kind of think, I mean, at least from what I've seen, you just kind of use optimization. Like, for example, in this case, you'd minimize the cost function to find like an optimal, like a best fit line, for example, if you're classifying or something. So as far as I know, it's just another tool you use inside machine learning.
That is a 100% true statement, but we didn't quite distinguish the difference yet. So optimization is clearly a subset of machine learning, but that means there's more to machine learning than optimization. What is that more to it? I'm going to give you a huge hint. It's on the screen. Generalization. What does that mean? That means I don't only want my algorithm to perform well on the data that it's given. I want it to perform well on data that it has not seen. Okay? That's the underlying premise of generalizing, general intelligence, like us. You teach me addition. I've never added together 1,754 and 1,200, whatever, these two, but I know how to do it now. I can generalize from the fundamental principles of addition to solve more difficult problems. That is the underlying difference between optimization and machine learning. So, in the field of machine learning, we need tools to be able to explore and quantify this concept of machine learning. So what we're going to look at are the 4 fundamental things to explore this concept. We'll briefly try and go into a little intuition about them, and then we'll move on. This is essentially the heart of machine learning. So this can be a little complicated, but I want you to understand, to know where to look. All right? You understand this is the difference, and in the future, if you need, these are the buzzwords to look up to understand more. But I'm going to help you see the difference for starters. The fundamental thing that everything is built upon is this concept of capacity. I'm going to give you a very simple example of what that would be. Capacity is essentially the representative ability of your model. So what do I mean? I mean, my model now is y is equal to ax plus b. How many parameters do I have in this model? 2, a and b. And I'm trying to map one variable to another, and I can choose any value for a and b that best describes some data. But let's say my data looks like this. Okay? Now, I want to somehow fit this model to this data. All right? There exists no such A and B such that I can fit a straight line through this data. Okay? So the capacity for this model is insufficient to represent the true underlying variation in the data. So what I need is a more complex model. Then we can fit the data nicely with a quadratic. Okay? But what happens if I get a model that looks like this? 90, who cares, right? Of a sub I, x, yeah, power, boom. So the 90th degree polynomial. What's that going to do when I try and fit it to this, right? How many oscillations does a 90th degree polynomial have, right? Remember that from pre-calculus?
At least 89.
N minus 1, very good. So this thing's going to go like this. It's going to pass, and it's going to pass through every single point. It's going to have 100% accuracy in predicting this training data. And we're going to be like, man, we did such a good job. It's 100% accurate. But then you give it a point it's never seen before, like right here. And the true model says it should be here, but this model predicts it to be way down here. So you then give it some training set, and it's going to do awful. Okay? This is the notion of capacity. And that's underfitting and overfitting. Underfitting is when your model has insufficient capacity to describe the intrinsic variation in your data. Overfitting is when you have way too much and you're oscillating all over the place, okay? The last thing is this magical term called regularization, which everyone's probably heard of in some form or another in multiple fields. It's hard to really define exactly what regularization is, but in machine learning, the definition that we've sort of agreed upon and found in a couple textbooks is, it's anything that you do to your learning algorithm that improves its ability to generalize without decreasing its training accuracy, okay? So let's show what I mean by that. So this plot more or less summarizes it all. The bottom axis here is our capacity for our model. The vertical axis is our error. So what we want to be able to do is to find the optimal capacity for our model such that our red line, which is our generalization, is as low as possible. So remember, if the capacity is too low, we can't fit the training data or the generalized data. I mean, that straight line can't fit that parabola no matter what. We increase the capacity slightly, and then we get a great fit here. It's doing great on the training data and great on data it hasn't seen before. But if we keep increasing that capacity, it starts oscillating all over the place, and it's doing bad on the data it hasn't seen before, but it's fitting perfectly to everything that it has seen, okay? So this is the goal in machine learning. How do we choose the perfect capacity for our model? All right, and so here we see a little bit more, detail. So here's the figure that I more or less wrote on the board. This is, so what is this describing? Optimal, and then overfitting, okay? And in machine learning and statistical language, we call this bias and variance, okay? So here's an example. If you have low bias and low variance, you're guessing great every single time. If you have low bias but high variance, then that means you know what the right idea is, but you're not able to quite nail it down. There's too much variation. If you have high bias but low variance, you're really good at not getting the right answer. You have some misconception of what's going on, and you're convinced it's this thing that's just not at all right. And then if you have high bias and high variance, you should just, change profession, because you have to intentionally construct a model that just does poorly on both of those. That's hard to do. You can't even really do that by accident. All right, so this is the shotgun explanation of machine learning and the difference between it and optimization. Generalization, we explore with these notions of capacity, underfitting, overfitting, and regularization. And people do entire dissertations just on regularization techniques, etc., finding optimal capacity for these different models. So that's the underlying nuts and bolts, okay? So we're going to move on, though, now. And now we're going to talk about neural networks. This is another one of those buzzwords that people see, and whenever they talk about deep learning machine learning, we need to really know what it is, okay? First, let's just take a few minutes to just motivate what it is, okay? It came about in 1950 something. McCulloch and Pitts, they made their first perceptron model about a neuron, and it was based off of what we had been discovering about the anatomy of neurons, the first artificial neural network. Neural networks, neurons actually are quite simple in their general functionality. You have a soma, which is the cell body. You have an axon that sends the signal from one neuron to the next. And then the receiving neuron has things called dendrites that receive the information. And the key magical thing that lets us all learn and lets us adapt is this thing called a synapse. The synapse is where the information goes from one neuron to the next. And it has an ability to change the quote-unquote efficacy of transmitting that signal. So if this guy sends a signal of 1, this might have an efficacy of 50%. So this signal of 1 just got turned into 0.5 when it came over here. All right, now every neuron has thousands and thousands of dendrites, and the axon branches out into multiple branches. These things connect recurrently with different delays, and it's amazingly complex. However, we decided to just make a super simple approximation to it, and it's like this. We have neuron 1, neuron 2, and we model the synaptic efficacy with a simple number called W. That's the weight. It's the ability to transmit a signal from one neuron to the next. So a neural network, in all honesty, is just a function that takes some input and it gives you some output. There's no magic, there's no sorcery. Neural networks can't learn. Neural networks they just take some input and they give you some output, just like this. So you have some nonlinear function, some nonlinear activation function here. That's where the data gets aggregated at the axon hillock here, and then once it reaches a threshold, bam, it fires and sends the signal down to the next neuron. That's what we're modeling here with this F function. But internally, it's just the signal from neuron 1 times its synaptic efficacy. You know, you're weighting the signal from neuron 1 plus the signal from neuron 2 weighted by his synaptic efficacy. They all come into some neuron, and if it reaches the right threshold, boom, he sends the signal down, okay? So a neuron is just a function. A neural network is just a function, input, output. So that's the first myth that I guess I'd like for us to make sure that we have clear. Neural networks are functions, input, output. There's no magic, they don't learn, they don't do anything. They get some input, they give you some output, all right? The next one, backpropagation. Who can describe what backpropagation is?
This looks like graph theory.
Yes?
So, is it instead of like starting where you have all the components and then you go and find the answer, you start the answer and then you go and break it up by components? So the other way?
I'm not quite sure I followed that explanation, but given that I didn't quite understand you, maybe. Yeah, yeah?
Is it basically where you run the function and then try to figure out, going back through all the layers, what the best weight for each neuron would be?
Close. That is so I'm really glad you said that, because that is the misconception. So the idea is that backpropagation does not find the optimal set of parameters for your network, the W's, the weights. Backpropagation takes the derivative of the weights with respect to some cost function, period. It is not a learning algorithm. It doesn't teach your network to do anything. It is merely an algorithm to calculate the gradient of the weights with respect to the cost function. Why? Well, because any of you that have taken optimization theory, you know that if I want to find the optimal theta, I use gradient descent or something. Theta sub I plus 1 is going to be equal to theta sub I minus the gradient of the cost function evaluated at the theta sub I, you know, with your x and your y. Right, so this gradient of the cost function with respect to, this should probably really be here for notational succinctness. Okay. The gradient of your cost function with respect to theta I, that's backpropagation. It's complicated. How do we take the derivative of all these parameters with respect to some cost function? That's what the algorithm does for us. It doesn't learn anything. It just gives you the derivative of the weights with respect to the cost function, okay? And that's what we see here. Information propagates forward, and then you take this delta, which is the derivative of that something. Okay. Information propagates forward using the rules that we just described, multiplied by all the weights. You get some output, you take the derivative, and you change the weights. You find the derivative of the weights with all the functions as you go backwards, with all the weights with respect to all the weights as you go backwards, and you use that as the input into your optimization routine. All right, and then we finally optimize. This is the learning process. Okay, you have your function, it does something, you find out how far off your function was from doing what you wanted it to do, and then you make it do that thing better. This is the learning process, okay? This is what allows you to update. So these are different optimization algorithms, and this is just a brief comparison of what they do. Optimization says, here's some cost function surface. This surface is, you can consider the z-axis to be error. So you want to go down to find the lowest possible point on this surface, which means you're minimizing the error. And once you get there, you just look at the value of the parameters that got you there, and those are the W's that make your neural network do the best at whatever your cost function is trying to get you to do. I'm sorry?
Oh, I was just wondering, does it only find local minima or global minima?
That is one of the biggest questions.
In this case, I was wondering if it would go backwards to that blue on the left side.
Great question. So that is one of the problems that it will plague us forever in optimization, is the difference between local minima and global minima. And that's this idea, that I have some cost function surface. This is the optimal place to be. But if I start here, for example, I take the derivative, I go in the direction of steepest descent, I go here, then I go here, then I go here, and then I'm here. I take the derivative everywhere, and it's like almost zero, so I'm in a great place. I think this is good. But this isn't really good. This is what's called a local minima. This is the global minima. So how do we distinguish between this and this? You get a PhD in optimization and come up with all kinds of crazy theories. You have stochastic approaches, you have exploratory approaches that let you actually sample different places. Choosing better initialization, initial conditions is one of the things. Like, so what if instead of starting over here, I started right here? then that would be great. So what are the techniques to give us the best initial condition to start from? This is considered regularization. Anything that helps modify our initial conditions to improve generalization there. All right, so yeah, that's the second big takeaway. The learning algorithm in neural networks is as follows. You have a function, you give it input, you get output. You take the derivative of the parameters of that function with respect to with the derivative of the cost function with respect to the parameters of that function, and then you make that function do better by updating the parameters such that it minimizes the cost function. And you do that over and over and over and over and over again. You can equate that to showing me a flashcard and I'm like, 7? You're like, no, it's 4. I'm like, oh, okay. Show me another flashcard, I try again, and you iteratively allow me to improve over time with more experience, okay?
So on that function that you draw on the board, theta I plus 1 equals theta I minus the gradient of the function at theta I. What does theta I mean again?
It is the ith step, so it's great. I'm taking steps as I move along the cost function, each of those little points that I wrote. So I have I'm at this point theta, I take one step, I get theta 2. Now I take another step, I get theta 3, theta 4. And you keep going until the difference between your thetas gets really small, which means that you're getting close to some minimum there, and you're not really moving much anymore, you're getting stuck at a minimum. All right, that's the premise of optimization. All right, so now something a little more interesting. Let's sort of take a look at the guts inside of our neural network. What is a neural network actually doing? Okay, so here's the model that we just described earlier. This is a linear classifier. We have an xy coordinate, and we'd like for f to be able to classify this as either one function or another. But f has a linear activation function. There's no nonlinearity here. But the problem that I'm going to present here is that our input data looks like this. And this is what happens. That's the best we can do at separating those two curves. So my question to you is, what is our algorithm suffering from? You got it. Very good. There are not enough free parameters, there's not enough capacity in our model to truly represent the true variation in our data set. So we have to increase capacity. So we do that by adding another layer. And then we add a nonlinearity to that layer, hyperbolic tangent. So this is going to be super cool. This is one of the things that really excited me. What you're looking at right here, is the xy space with the output of f. So each of these points over here is the xy space, and then the color is what f predicts that it belongs to. So that's cool. But the question is if this right here is just a linear classifier like we had before, then how is it somehow able to separate these things if it wasn't able to do it before? What is this layer here doing that lets it separate these things? I have a linear classifier at the end, so I'm separating things linearly. Somehow I'm able to get this. So what we do is we visualize this space. So instead of plotting x, y, and then the output of f, we're going to plot the transformed x transformed y and look at the output. And this is super cool. What the neural network is doing is creating a homeomorphism. It's transforming the space such that it's able to linearly separate those two curves. And that opens up a whole new branch of research for understanding neural networks. Differential geometry, studying how that stuff works. Yeah?
Okay, so basically what you're saying is, instead of directly trying to curve around those spots, it's going to take the entire space, it's going to squish it up, it's going to just morph it around, such that we can now make a straight line between those two, where we couldn't before with those, because those are just curving too much.
In a nutshell. There's some more details involved, but in general, another way that I would explain it in neural network machine learning lingo is you're learning a representation that allows the problem to be solved easier. So what you're doing is you're taking all of these points and you're transforming them. You're learning a more succinct representation so that you can class. So here's the analogy. I'm going to do an experiment. Okay, what's your name?
Morton.
Morton. Can you describe a face for me?
Round.
Good start. Sometimes. What else?
Irregularities on the side for ears.
Ears. What else?
Nose. Eyeball.
And mouth. Exactly. Everyone would have said the same thing. So what we did, and now let's think for a moment. How many features are there in faces? You've got little cranial bone here. You got like little imperfections in the lips and thicknesses and little hairs and maybe a little jaw, like an earlobe. Why didn't you say earlobe or something, right? Why didn't you say eyelash? Well, there are eyelashes on faces. Yeah, but why isn't that useful in categorizing a face? That's the whole the field of representation learning. What are the most descriptive features of some thing that allows us to identify it? Okay, and that's representation learning. What we did is we took this face, which is incredibly complicated in some super high dimensional space, and we reduced it to a lower dimensional space of features that describe the faces the best they can. And you can learn this. If I take pictures of hundreds of thousands of faces, and then I try and find, I do a feature extraction to find out what the features are that best describe it, it turns out it's eyes, noses, and mouth. And they've even done neuroscience experiments where they do eye tracking on people when they present them faces, and within milliseconds, the first thing that they do is eye, nose, mouth. Eye, nose, mouth. Humans, to identify faces, we look at eye, nose, mouth. These are the most descriptive features in representing faces. That's what this is doing. It's taking these points and transforming them into a new space that allows it to solve the problem of classification easier, which is what we do and the brain does when we look at things as well. If I say, look at this and I show you a picture of a tiger, and you're like, yeah, that's a tiger. How do you know? It's got hair and a tail. So do dogs and cats, right? There's certain features that clearly define what a tiger is. Yes?
If you're taking a function and pushing it to another space just so you can evaluate it easier, how do you determine what space is the most optimal space to transform it to?
Great question. That was the underlying question for my dissertation research. And regrettably, the answer is it is task dependent, and there does not exist an optimal feature space for all. It's my current contention. This is still subjective, but there does not exist an optimal feature space for solving every problem. It's task dependent. And I guess an analogy that I would give is, let's say that I gave you audio, and I wanted you to do a speaker recognition. So who is speaking? In the task of deciding who is speaking, their tone of voice matters, inflection, the volume, etc. But what if all I wanted was transcription? I no longer care how loud they said the words or anything. All I care about is the phonemes and where they are separated from one another. So each of these tasks are solved more easily with different types of features. So regrettably, the features that we learn to solve a problem are task dependent. And the way the human brain does it is something that we theorize is called transfer learning, where, for example, I learned what a car is by learning the wheels and its functional relationship to the car, and now I see a bicycle. And I'm like, what is this? I've never seen a bicycle before. And I go, well, it's got wheels. Cars have wheels. Maybe this is used for transportation. Right? That's transfer learning, taking something that you learned in a previous problem and applying it to a new one. So, yeah, that's super fun. Maybe we can talk more a little bit later. Yeah, that's my whole research. I love that stuff. So, let's keep going. So, neural networks are often called this big black box, right? Essentially, it's just a function that takes some input and gives you some output. Now, what's really important and special about these black boxes is there's something called the universal approximation theorem, which says that a neural network theoretically has the capacity to learn any function. There's a lot of caveats that make this particularly difficult. We won't go into those, but the idea is that this is the sort of theoretical underpinning that got people really excited about neural networks and trying to really understand how we can get them to learn these functions. If it can theoretically learn any function, how do we get it to do that? So, unfortunately, because it has this sort of convoluted magical idea to it, people call it, the black magic. Jeffrey Hinton is the, quote-unquote godfather of AI. And yeah, he even says there is some black magic involved. It can be complicated. However, this is another point that I'd like to demystify. The black magic is not in the neural network itself. The black magic is not in backpropagation. It's not in optimization. We know how all of these things work. They're pretty clearly well defined for the most part. But what we really don't know that well is how all these things work together in concert and can orchestrate all of these simple components that allow us to achieve these amazingly complex things. That part still eludes us a little bit. And XKCD had a great comic, if any of you have looked at this stuff before. He said, so, this is your machine learning system, huh? Right down here. He's like, yep. You pour the data into this pile of linear algebra, then collect the answers on the other side. He's like, well, what if the answers are wrong? He's like, you just stir the pile until they start looking right. And unfortunately, that really summarizes the field quite nicely, because I can't tell you how many hours I put into just tuning parameters and tweaking the learning rate and changing the regularizing coefficient and blah, blah, blah. So there's a lot of that going on, unfortunately. But there's intuition behind how these things work. And it's not just guess and check. It's a guided intuition. One thing we can be excited about, though, is that this black magic is being dispelled, for lack of a better word. So there's a research group called DeepMind, and they published a paper recently, well, kind of recently, I think it was a year or two ago now, Cognitive Psychology for Deep Neural Networks, a shaped bias case study. So they're using cognitive psychology concepts to help us better understand what neural networks are doing. It's almost like applying things we use on humans on neural networks because they're getting that powerful, which is pretty exciting. Not the biggest fan of DeepMind. They kind of sensationalize AI and they contribute to the whole. You guys saw that thing where like Facebook and their computers invented their own language and oh, they're going to take over. That's such hogwash. It's just media sensationalism. It wasn't even anything kind of like that. And unfortunately, things like this sort of contribute to it. But that's why we are educating you here today to know the basics so that you won't fall for such stuff. All right. Okay. So now we know machine learning principles, we know neural networks, we know what the difference is between optimization and machine learning, it's generalization, and so now we have this field called deep learning. So the question is, what is deep learning and how does it fit into this perspective? Any ideas?
It's like machine learning, but deeper.
That's almost the exact definition. That is even closer to the exact definition. The term came about from this idea of deep learning emphasizing that you can now obtain deeper neural networks, as he said, multiple layers. Also, if you can most neural networks are represented as probabilistic graphical models, and they're very deep node from one probabilistic node to the next. And so these sort of concepts contributed to this term deep learning. Unfortunately, a deep neural network, or deep learning, is machine learning on neural networks with 2 or more hidden layers. That's it. So it's basically just machine learning with neural networks. I'm sorry to disappoint all of you. Yeah.
Why 2 or more? Why is exactly 2 not considered deep?
Ask Jeffrey Hinton. Honestly, I put an asterisk, I think. Yeah, I put an asterisk because that's Jeffrey Hinton's, the way that he defined it, and given that he more or less kind of invented the field, I'm just going with his definition for now. But there is actually no accepted academic definition. You know, it's many layers, and Jeffrey Hinton's like, let's just say 2 or more, classify the field. You know, everybody wants to classify things. So, in a nutshell, it's machine learning on neural networks with lots of layers. That's all it is. Incorporating everything we discussed, capacity, regularization, all of these things, it's just machine learning on neural networks. No more sorcery to it than that. So, let's just take a super high-level look at the field of deep learning and kind of the more buzzwords that you guys have probably heard. The first and foremost is you get this deep feed-forward neural network, multi-layer perceptron. You might have heard of both of these things. This is simply, you have input, you have hidden layers, and then you have some output. And you map that output to whatever you want. It can be classification, it can be regression, it can be you're trying to transcribe some text, whatever you want. This is just a simple feed-forward neural network. You then have deep belief networks, which is where you take some input and it has stochastic nodes. These things are intrinsically probabilistic. And it turns out that this cutting-edge machine learning, everything is better cast as probabilistic. Yes?
This might be a basic question, but what does probabilistic mean?
Probabilistic means not determinable. So that means that if I were to do something over and over again, I cannot get the exact same answer every single time. It's just a great way to just make a little plug, okay? From everything we've been learning about neuroscience and machine learning, epistemology, knowledge, and everything, there does not exist a clear, succinct, and objective way of defining more or less anything. And I really like this because it really has implications in so many facets of life. People who like to tell you exactly how politics should be, or exactly how this economic situation, or money, or religion, they're just like 100% sure. Everything we've been learning about machine learning and neuroscience says that we can't say it with certainty like that. Every sense that you have, vision is you're seeing the result of something having been there. A photon bounced off of it. You're not seeing it, you're measuring it. touch and tactile. It's just electrons and magnetic fields pushing against it. You're not actually touching anything. You're just feeling the result of something having been there. Smell, molecules coming off of something. Hearing, sound waves coming off of something. All of our senses are approximations to reality. And it turns out that casting these things in a probabilistic framework allows us to better approach this notion of generalizing intelligence because it's actually what's happening with us. So, a little segue, but I think that's important. Then deep convolutional neural networks, that was motivated and inspired by the visual cortex of the human brain. All right, so in the very back of the head, we have the photoreceptors in our eyes come through the optical chiasm, split and separate, go into both sides, and then hit into the back of the visual cortex there. And then it propagates through different layers we call V1, V2, V3, etc. And given that we've observed that, we were inspired, and by we I mean Jan LeCun, to develop convolutional neural networks. And the idea is just that there's a hierarchical processing of information. And the intuitive definition is this. If we talk about faces as eyes, noses, and mouths, etc., how do we go from a whole bunch, hundreds and thousands of tiny little photons to eyes, noses, and mouths? Well, you start off by going from hundreds and thousands of photons to tiny little edges, little lines. That's all. You just get a bunch of little edges at different angles. Then in the next layer, these edges combine to create little curves. And then in the next layer, these curves combine to create small little shapes, circles, and different lines, etc. And then in the next layer, they become eyes, noses, and mouths. And then in the next layer, all the eyes, noses, and mouths combine to identify different faces and different people and different characteristics. And that's the inspiration behind that. And then recurrent neural networks allow us to incorporate this concept of memory or temporal dependence. Because in reality, nothing is static like that. It's not like I open my eyes, look at a cat, and close my eyes, and never open my eyes again until I see a picture of a dog, right? I mean, there's this smooth continuum between everything that we see. And recurrent neural networks are a way for us to sort of model that temporal dependence. And then here's the cutting edge. You guys have probably heard about this stuff in the media, and Twitter, etc. You've got GANs, generative adversarial networks, and variational autoencoders. So generative adversarial networks, they work as follows. It's basically the idea of counterfeiting money. That's how people describe this. You have some guy who wants to counterfeit money. So he's going to go ahead and give it a shot. He's not very good yet, though, so his money's super easily detected as counterfeit. And there's some detective over here who's also not really that good yet, but he wants to learn. So he's like, this is actually counterfeit. And then he tells him why it's counterfeit, and so this guy comes over here and he improves his ability to do it. And then he gives it to the detective, and then the detective gets better at detecting counterfeit. And then it goes back and forth where this person's trying to counterfeit better and better, and this detective is trying to detect whether it's actually counterfeit, until eventually the counterfeiter is reproducing money that's essentially indistinguishable from actual money. Okay, and that's the goal. And that's learning the underlying distribution. I'm going to be reproducing faces until the new faces that I invent are indistinguishable from the actual faces that are generated from the true underlying probability distribution. Yeah?
So going back to your example with the counterfeit money and the detective, why not just get a detective, and this might be I guess, kind of a naive question, but why not just get a detective that's good at detecting counterfeit money from the get-go, and then have the person who's trying to counterfeit that money just keep on getting advice from that detective that's already good.
So you can do that, and that's called supervised learning. Right, where you have labels for those things. What's good about this, well, the problem with that, or a problem with that, is that introduces bias. Right? It's learning a specific type, and the detective needs to be able to adapt with new experiences, and to be able to learn along with the counterfeiter. Though that is a great question, though. That's an area that we can talk about for a long time. Yeah?
So, essentially, GANs are able to create their own data?
Essentially, yeah. And by essentially, we mean, yeah, 100%. Yeah. So the other thing is variational autoencoders. This is actually my area of research, and I apply this on computational neuroscience data, because this is also representation learning. We take some data, we reduce the dimensionality to some stochastic nodes in some latent space, and then we try to reconstruct the data based off of this lower dimensional representation. Yeah?
Would you mind quickly explaining what stochastic means?
Stochastic's probabilistic. Deterministic and stochastic is probabilistic and non-probabilistic.
So it's basically the opposite of probabilistic.
No, stochastic is probabilistic.
It is, okay.
Yeah, they're just different words for the same thing. Sorry. Yeah, but it's a good question. And yeah, so it's generative, which means I can look at this latent space and just take a sample. And it turns out that if we do this on faces, each one of these nodes are going to account for like nose size, mouth, eyes, how far apart the eyes, the orientation of the faces, lighting, where the light is on the face. And so if I generate a bunch of faces by slightly changing one of these noses, you'll see that the face actually just like slowly turns its head. So this is learning the intrinsic descriptive features of faces. This is the underlying notion of a latent variable model. So we have a latent representation of the face. That's what we call it. These features are learned in this latent space. And so you can just sample from latent space and create a face. And yeah, so you can theoretically just generate new faces. However, it can only generate faces based off of the features that it's learned from the faces it's already seen. And that's a really interesting insight into our own creativity. We can't really, what if I'm like, hey, imagine something you've never imagined before. What does that even mean, right? Like, anything that you could ever imagine is based off of some sort of evidence or data that you've seen, you've combined it in some way, and you've created something which is allegedly novel, but it's all built off of fundamental components that you have perceived at one point that became some sort of representation in your head. And it's something that's really important. I think it's very humbling to think that way. Yeah, think about a musician. Oftentimes it's like, oh, I was inspired by this. So basically he took music and then just made new music based off of that music, right? So nothing's just truly invented out of anywhere. Yeah, we won't really get into that, but yeah, so here's the probabilistic graphical models like I talked about. This is the architecture for a variational autoencoder. Let me just show you actually a couple of cool examples before we wrap up, and then we'll ask some questions. So yeah, this is what the variational autoencoder does. So this is my research, we won't go into that too much. This is the latent space. Okay, so here's something kind of cool. So this is some work that I've had some of my undergrads working on with me, and I think they're actually in here. Cameron, my man Cameron right here, yeah, so one of the HackFSU volunteers doing good work for you guys. He works in the intelligence lab with me, and he's been helping work on these projects. So we want to know how it's learning. How is the variational autoencoder learning these representations? So we create a synthetic data set of small Gaussians and large Gaussians. So we know the variation in the data set because we created it. Large and small, that's it. So what we do is we pass it through the variational autoencoder, and while it's learning, we visualize the latent space, right? And that's the lower dimensional space there in the middle. And it turns out that these are the kinds of things that happens. First, it learns to separate based on size, right? So those are the two classes there. And we get that the larger Gaussians have a tighter cluster in latent space, and the smaller Gaussians have a larger cluster in latent space. And then it slowly learns the noise, because you always have to add noise to things, because nothing in reality is perfect. Everything has noise, and as we talked about, and everything's an approximation, everything's subjective. So, yeah, so this is just giving us insight into how it's learning. We're watching the learning process actually taking place here. We can also do it in one dimension. What if we have a one-dimensional latent space? And we can watch it learn and see the size of these distributions. We can look at the the variance, the tightness of the cluster, which has to do with the amount of variance that's actually in each of these features describing the data. So it's really cool. And then I think at the end we have, an example of what we talked about before. So here's a variational autoencoder trained on a bunch of faces, and then you just change one latent variable, and it slowly starts morphing these faces based on these features. So one particular node is accounting for smiling. So you have a face, and then you change the smiling, and then it goes from smiling to not smiling without changing too many other features.
That's insane.
Okay, so this is the idea of, this is where the cutting edge of our knowledge currently is. We have a bunch of data that comes from some true underlying distribution, which we never really know what is. Our brains and our current neural networks that we're working with are trying to approximate these underlying distributions as best they can, to learn the features and the variation, the variational properties of these underlying distributions. So, yeah, I'm just going to summarize with that. Neural networks are functions, input, output, okay? They don't learn. Backpropagation is an algorithm for calculating gradients of the cost function with respect to the weights. All you get is just a set of numbers. You don't do anything, it's just a set of numbers. Optimization is basically taking one step across that cost function to update the thetas from theta I to theta I plus 1 like we showed over there. All of those things together is the learning algorithm. You have your function, which makes a prediction, you take the gradient, and then you optimize. That is learning, okay? Deep learning is just machine learning on neural networks of multiple layers, and AI is super cool. Check out what we can do. And that's the end of my talk. And I would welcome questions, please. And thank you for your attention, and thank you for coming. Yes?
So
resources or anything you recommend for us to look at?
Absolutely. There are so many, it's overwhelming. And often it's actually kind of hard to find the right ones to get started. For my highest level recommendation to get started, I would get started with the principles of machine learning. So on Coursera, everyone's probably heard of Coursera, edX, Udemy, etc. Coursera has a great course by Andrew Ng at Stanford, just called Machine Learning. And that's a great course to get started with.
What did you say it was called again?
It's just called Machine Learning by Andrew Ng from Stanford on Coursera. It's a great place to get started. You can ask more questions from there. Yes?
What's your name?
My name is Nathan Kroc. Hello, everyone. Any other questions? Yes?
It's not a question, but I really liked your presentation. I think you make a tremendous teacher.
Thanks. That's kind words. I appreciate that. Glad you enjoyed it. More questions? Yes?
So for dealing with optimization, what's your experience with something like learning rate annealing?
I wish Brian were still here. Is Brian still here? That's his whole line of research. But he'd probably be able to talk to you better about that. So, yeah, so who knows what that is? High level overview. What is that?
Okay, yeah, so learning rate annealing, basically, as you're trying to optimize your function, you're going to change the step size that you take up or down the gradient.
Correct. So, in general, it's usually a good idea to have the learning rate get smaller and smaller as you learn. Okay? Why? Well, because as you get closer and closer to this minimum, you want to take smaller and smaller step sizes. If you have your step size is constrained to be super large, but the minimum is here, you're essentially just going to jump back and forth across this minimum, and you can never really get any lower. So you need to get the step size to be smaller and smaller and smaller to let you get closer and closer and closer to the minimum. So annealing your learning rate is a common practice, and they call it a learning rate decay, and that's a common practice for most people who are in the field. However, how quickly you apply it and on what algorithms, that's an active area study, and that's a regularization technique, and that's something that he is studying with one of the other researchers in the intelligence lab as well. Any other questions? Yes, sir?
Can you talk a little bit about pre-processing data?
Oh, God, I wish I didn't have to, but yeah. So 90% of machine learning is just data grunging and just data pre-processing. You gotta clean it, you gotta whiten it, you gotta format it in a way that's digestible. I mean, so what if I want to operate on words? I can't just put words. I mean, neural networks are numbers. It's linear algebra. How do you turn words into numbers? You know, what if I want to operate on pictures? Well, pictures, especially like colors. How do I? Well, it turns out that each of these is an RGB value, etc. You can have different channels in your matrices, and you can go to gray or keep it in color. And so, pre-processing. If you want to be good at machine learning, you have to be really good at data pre-processing. Unfortunately, that's the majority of the work. And you can make a tremendous amount of money just being really good at operations. Pumping data in and out of databases and cleaning it and making it easily accessible for people. Tons and tons of money are being dedicated to that at Google, Facebook. When I was at Facebook, the database team, the people who worked on the database were like 3 times the size of the machine learning team. And in machine learning, we were trying to just get access to certain things from the database quickly so we could ask quick questions. But if I have to waste 5 or 6 hours writing scripts to get this data, and then I have to randomly sample to get this, to do this, I forget what my question was in the first place, it's 5 hours later, right? So you want quick iteration, turnaround time to experiment and build intuition. So operations and data grunging is very important and a very lucrative field, despite how miserable